Hey, here's some problems by popular request from section 8.8 in your calculus book. We're going to do 5, 7, 15, 17, and 19. And see how we feel after that. Hopefully pretty good. Number 5, I have the integral from 3 to positive infinity, 2 over x squared minus 1 dx. Popular wrong move here is to say, oh, that's just the antiderivative of that. It's natural log of x squared minus 1, or 2 times that. But it's not. That wouldn't work if you think about taking the derivative. Do a little scratch work here. If you had the function f of x is equal to 2 over x squared minus 1, if I had f of x is equal to the natural log, or let's say 2 times the natural log of x squared minus 1, and I took the derivative of that, that would give me 2 times the derivative of natural log whatever is 1 over whatever times the derivative of what's inside. So the problem with that is, with approaching this problem that way, that doesn't work. You'd have to have a u substitution here. The only way that the antiderivative of something is equal to natural log of something is if it's 1 over that something to the first power, or you can u substitute it to that. So it ain't that. Which means, well, think about other options that we have. It doesn't match up to like an inverse trig or something. So, well, I can factor the bottom, so doesn't that mean that I could turn it into one of these? So if that's the case, then let's see, that'd be ax minus a plus bx plus b all over the common denominator. So that means that a plus b, those are the x coefficients, but I don't have any x's there. So a plus b must be 0, and then minus a plus b must be 2. So if I add those equations together, they're all set to cancel that out. I get 2b equals 2, or b equals 1. If b equals 1, then a is equal to negative 1. All right, so I'm going to rewrite this. I'm going to write the positive one first. We'll see why in a minute, I think. So now I'm going from 3 to infinity. I'm going to bring that 2. Oh, no, I used the 2 here, so that 2 doesn't need to go anywhere because I used it here. So let's see, I'll do the b1 first. So that's 1 over x minus 1 minus 1 over x plus 1. Right, and taking the antiderivatives, that gives me natural log of x minus 1 minus the natural log x plus 1 from 3 to infinity. Now, if you just try to plug the infinity in right now, you're going to get kind of in trouble here. Whenever I have natural logs and subtraction involved, you need to use your natural log rules to try to simplify this. That's x minus 1 over x plus 1 from 3 to infinity, and see what happens what we get now. See what happens what we get now. It's not really a very well-formed sentence, is it? So if I plug in infinity, if plugging in infinity really means like finding the limit as x approaches infinity. So the limit as x approaches infinity of x minus 1 over x plus 1, that limit's equal to 1, right? Same power, top and bottom, so it's the coefficients. That's a very old, like chapter 2 limit for us. So I get the natural log of 1, because this is approaching 1, minus, when I plug the 3 in, the natural log of 2 over 4. And using what we know about logarithms, that's 0. Negative sign can come in and flip that over. I get here that that converges to the natural log of 2. All right, number 7. Let's see what we got here. We have the integral from e to infinity 1 over x times the natural log of x cubed. They use that little notation where they put the cubed in there, but it means the same thing here as it does with trig functions. Has to mean that. So I think about how could I take the antiderivative of this, and this looks like u substitution. So if I made u equal to the natural log of x, remember you always choose the u to be like a what's inside type of thing, then the du is equal to 1 over x dx, and I can see that I'm in business there. So rewriting this integral, my numbers here are not going to be x numbers. Now I'm going to turn them into u numbers. So u equals the natural log of x, so when I plug e into that I get 1 here, and then the natural log of infinity, that's still infinity. Alright, so what does this turn into? This turns into the 1 over x dx just turns into the du, and then I have 1 over u cubed, or u to the negative 3, maybe better for calculus purposes. And the antiderivative of that, bump the exponent up 1, and then divide by the new exponent. I'm going to put that on the outside. That doesn't need to be in here confusing things for me. So that gives me negative 1/2 times 1 over infinity squared minus 1 over 1 squared. And that is what we're hoping for. That's 0, so that gives me positive 1/2 for number 7. Number 15, see if we can sneak that in here in the bottom of this page. Let's see, what do I have? So from negative infinity to positive infinity, of x over x squared plus 3 squared dx. This is another u substitution. So u is equal to x squared plus 3. That's the what's inside looking thing. We need a 2x on the inside, so I'll need a 2 here, which means I'll need a 1/2 on the outside. So rewriting this, looks like I have, when u goes, let's see, so changing this over to u numbers, I have negative infinity, plugging that in here, that's positive infinity squared plus 3, that's positive infinity. And then up top, I have positive infinity. And I can keep going here, but right off the bat here, that's a little funny, isn't it? So going from positive infinity to positive infinity, it looks like when I did my u substitution here, I'm getting the same thing here and here, so this should turn out to be 0. In fact, it is equal to 0. You can go back and look at this and think about why that might be the case, and it does turn out this is in fact an odd function where both sides of the integral are well defined, unlike in number 13. So this one, it does come out to be 0. Like if you did this from 0 to infinity, you would get an answer. And if you did it from negative infinity to 0, then you would get an answer, the negative of that. So when you go all the way, you get 0. And that's what's happening here. We can see that right there. Number 17. We have the integral from 0 to 4 of 1 over x minus 4 squared dx. You might look at that and say, wait a minute, is that even an improper integral? It is, because this function has a vertical asymptote right here. So it is indeed. So let's see. I'm going to go ahead and u substitute this. so that this will work for us. It's not a very exciting substitution, but it basically just shifts the thing over so I can find the antiderivative of that more betterer. Just kidding. It just makes it possible to do that. So 0 minus 4, these are my new numbers, 4 minus 4, and then here we have 1 over u squared, or u to the negative 2 du. The antiderivative of that is negative. We bump the exponent up 1, and then divide by the new exponent. I'm going to put that on the outside. I think it's easier that way. That's my preference. You don't have to. So I have negative, and then when I plug in 0 here, I get 1 over 0 minus 1 over negative 4. 1 over 0 is going to go to infinity, so this is divergent. No dice. As they say in Scotland, you cannae do that one, lad. Number 19. Here's another one that you might look at, and it might not strike you immediately as an improper integral, but if you think about for a minute the tangent function does indeed have a vertical asymptote at pi over 2. So if you wanted to imagine what's going on here, if this is at pi over 2, the tangent function's creeping up like this. So is this a well-defined area for us or not? Well, let's find out. So what's the antiderivative of the tangent function? Well, that, I don't know if you remember that or not. That's a little tricky to get to. But to get to it, remember tangent is sine over cosine, and then that suggests that maybe we can do a u substitution. If u is cosine x, du would be negative sine x. So I'm good, except I need a negative here, which means I need a negative on the outside. So switching that over now. So the cosine of 0 is 1, and the cosine of pi over 2 is 0. You could use that negative sign to flip those if you wanted to. Be a nice idea. And then this is u to the negative 1 now, after I do my substitution. du. So what's the antiderivative of 1 over x? Well, that's natural log. So I'm going to use that negative sign to switch things over. So I got natural log u from 0 to 1, and natural log of 1 is 0, minus the natural log of 0, and this goes to negative infinity. So this is trying to be some version of positive infinity, so this is divergent. But we tried. They can't say that we didn't try. And that's it. Those were the requested problems from 8.8.